Okay, so that wraps up commercial space. Now we're going to be talking about what spacecraft are used for, or applications. So, common satellite mission types or spacecraft missions kind of fall under three broad categories, and then I'll go into the subcategories. We have technology, which includes demonstration of engineering concepts, infrastructure, or using a gravity-free environment to demonstrate something. There are also classes of communications and surveillance, like DirecTV and GPS. And then there's also science. So our curiosity leads us to use space as a medium to demonstrate technology and advanced science, otherwise unachievable on Earth. Technological advancements may also be mixed with self-serving goals like communications and surveillance. Science data from satellites help us monitor the weather or combat climate change. Earth-observing satellites must orbit in space to sweep over large expanses of Earth's surface and atmosphere, or collect in situ measurements of atmospheric gases. A partial list of space system classifications include communication, positioning and navigation, weather, remote sensing, and launch. Astronomy, astrobiology, and planetary science are predominantly sciences for the sake of knowledge. As we mature into a spacefaring civilization, these sciences will become more pragmatic. On the top here, we have the Deep Space Atomic Clock, which I'll talk about later. And then here is a little diagram showing how all of these different vehicles are utilizing GPS, which are spaceborne technologies. So there was a question about, could we have a section including general payloads and examples? So yes, I've made a whole new section about that, and I'll present it here. Okay, so we're going to start off with different technology demonstrations that still constitute as payloads. All of the things that I was talking about, technology demos, communication, and science, all of those have their own pertaining payloads. So here is the MARCO CubeSat. MARCO is a twin CubeSat mission developed by NASA JPL to accompany the InSight mission that went to Mars. InSight stands for Interior Exploration Using Seismic Investigations, Geodesy, and Heat Transport. So MARCO's primary mission objective is to launch with InSight and independently fly to Mars to serve as a communications relay during InSight's entry, descent, and landing phase. MARCO represents a new type of deep space mission, CubeSats at Mars. MARCO is a 6U CubeSat, and I think this is the first time I'm saying U, so I'll define a single U is a 10-centimeter edge length cube. So there are 6 cubes in this CubeSat. The payload itself is a high-gain reflecto array and the communications subsystem. And there are some stats here that are good general facts about the spacecraft. Okay. Another technology demonstration that we talked about earlier, or I just briefly glazed over, is the Deep Space Atomic Clock, which will offer infrastructure in space. So the Deep Space Atomic Clock is a miniaturized, ultra-precise mercury-ion atomic clock for precise radio navigation in deep space. It is orders of magnitude more stable than existing navigation clocks, and it has been refined to limit drift to no more than 1 nanosecond in 10 days. That's pretty incredible. It is expected that a deep space atomic clock would incur no more than 1 microsecond of error in 10 years of operations. It is expected to improve the precision of deep space navigation and enable more efficient use of tracking networks. This project is managed by NASA JPL, and it was deployed as a part of the U.S. Air Force's Space Test Program 2 aboard the SpaceX Falcon Heavy rocket on June 25th of 2019. It became an active mission on August 23rd of 2019. And then as of June 2020, NASA has extended this mission through August 2021. So I think it's pretty clear here, the technology demonstration was the precision of a deep space atomic clock. And the payload itself is the clock, which is shown here. This is the payload. Okay. Another type of technology demonstration is additive manufacturing. The picture on the left, or both pictures on the left, show the first commercial 3D printer in space. And I just thought it was really funny that Lowe's is one of the sponsors here. But it's primarily spearheaded by a company called Made in Space. The Additive Manufacturing Facility, AMF, is the first permanent commercial manufacturing platform to operate in low Earth orbit. AMF is Made in Space's flagship technology on board the ISS, and its versatility and durability have made it a reliable source for government and commercial customers since its activation in 2016. It has produced over 200 tools, assets, and parts in orbit. AMF's legacy has been the foundation of our technology roadmap and manufacturing programs as Made in Space develops new capabilities that will leverage additive manufacturing in space for unprecedented applications. So the spacecraft in this case is the ISS, and the payload is the 3D printer that is on board the ISS. The ISS is this huge platform that has many payload racks, and so if you're ever interested in flying something on the ISS, it's probably one of the easiest ways to get to space, where there are standards to the way that these racks are configured, so a certain amount of volume and mass and electrical configuration. Yeah, so this is one of the payloads on board the ISS. On the right here, I think is a really cool technology demonstration. So for the future, NASA funds a demo of 3D printed spacecraft parts made and assembled in orbit with this little robot. NASA has awarded Made in Space a $73.7 million contract to demonstrate the ability of small spacecraft called Archinaut 1 to manufacture and assemble spacecraft components in low Earth orbit. The in-space robotic manufacturing and assembly technologies could be important for America's Moon to Mars exploration approach. So I can just geek out about this because I come from an engineering background, and technology, I would consider myself a space technologist. So yeah, I think technologies are meant to enable further capabilities, but ultimately science is the fundamental questions that we're trying to answer. Okay, and then there are other technology demonstrations like sample return. So here on the left is a video of OSIRIS-REx doing a touch and go maneuver on the asteroid Bennu to collect samples with that arm. And then on the right here, we have a technology demonstration on Earth for a proposed comet sample return mission. This video shows the bi-blade touch and go demonstration on a full-scale NASA spacecraft testbed, filmed in 2017. The spacecraft emulator, which was that huge frame with all the other supporting subsystems like pressurized air, that was all 2,200 kilograms, which is representative of a full spacecraft mass and inertia. Closed-loop control of the spacecraft emulator provides testing at representative touchdown velocities. The material sampled is MPAX, a comet simulant, with a strength of 5 megapascals cone pressure penetration resistance. So that's why that whole maneuver was so intense. So I got a question, are there any ethical or moral issues that have been brought up about mining resources from astral bodies? So to address the ethical, moral, or even political issues surrounding asteroid mining, President Donald Trump signed an executive order on Monday. I'm not sure if it was this Monday, but some Monday in recent past, that directs Secretary of State Mike Pompeo to seek further international support for the US policy that allows organizations to collect and use resources in space. The executive order establishes U.S. policy toward the recovery and use of space resources, such as water and certain minerals, in order to encourage the commercial development of space. In essence, Trump's executive order reaffirms a decision made by Congress in 2015, which gives American individuals and corporations the right to engage in commercial exploration, recovery, and use of resources in outer space. Trump is, well, he's not anymore, but he was going to seek other countries' support to protect companies which will make use of these resources. It's essentially saying outer space is a legally and physically unique domain of human activity, and the United States does not view it as a global commons. But administrations change. Space policy is still in flux, so I'm really not sure what the policy will be when the technology and the missions are real. So I think that one of the students in the class is interested in space policy. This is going to be a hot topic in the future and will continue to be in the foreseeable future. You can Google space policy commercial activity. Okay, another mission type is communications. Starlink is a satellite internet constellation being constructed by SpaceX, providing satellite internet access. The constellation will consist of thousands of mass-produced small satellites in low Earth orbit, working in combination with ground transceivers. SpaceX plans to sell some of the satellites for military, scientific, or exploratory purposes. Excuse me. Product development began in 2015. 2 prototype test flight satellites were launched in 2018. And then 60 operational satellites were deployed in May 2019. As of September of last year, SpaceX was launching up to 60 satellites at a time and aimed to deploy 1,440 of the 260 kilogram spacecraft to provide near global service by late 2021 or 2022. SpaceX started a private beta service in the northern United States in August of 2020 and a public beta in October of 2020. The payloads on board these Starlink satellites are K and E band phased array antennas. So it has to do with communications. So here is that outside is a rocket fairing, and then this is a stack of 60 or so satellites. This here on the right is a constellation pattern of the various satellites. So you can see that it's quite a knitted web. There are similar systems to this. So communications is a big game in itself. I'm just providing a single example, but other examples include Globalstar, which provides intersatellite communication and satellite phone communication, Iridium satellite constellation, Kuiper systems, OneWeb, and Orbcomm. But a word of warning, the early Starlink satellite was highly reflective so that you can see satellite glints with the naked eye. This effect was even more pronounced for sensitive observatories. So on the left, you'll see a signal pollution in a 333-second exposure taken from the Blanco 4-meter telescope at the Cerro Tololo Inter-American Observatory. 33-second exposure image by astronomers Clara Martinez and Cliff Johnson show at least 19 streaks created by a second batch of Starlink satellites launched in November 2019. You can also see the Starlink satellite train. You see these little blurs in nearly a line. And this is the view from the International Space Station. So the SpaceLink satellites have since been modified with a surface coating to be less reflective. What I want you to take away from this is your spacecraft can have significant impacts on the space community, whether you're impacting astronomical observations or astrobiology when it comes to planetary protection and landing on other planets. We have a responsibility as a community to ideally leave no trace, like in nature, and to be respectful while operational in space. Orbital debris and accumulation is a problem. So many satellites, there are two things that I want to mention about how to be responsible. You can have non-reflective surface coatings, and you can also build in end-of-life missions where you leave some propulsion in your satellite to re-enter Earth's orbit and burning up that satellite so it doesn't just float as space debris. This helps mitigate debris collisions, which harm all satellites in that band of orbit. And that's been increasingly a problem for future missions. Okay, so now I'll go on to science missions. The first that I'll talk about is astronomical observations, which rely on remote sensing through electromagnetic waves. Astronomers use a number of telescopes sensitive to different parts of the electromagnetic spectrum to study objects in space. Even though all light is fundamentally the same thing, the way that astronomers observe light depends on the portion of the spectrum they wish to study. For example, different detectors are sensitive to different wavelengths of light. In addition, not all light can get through the Earth's atmosphere. So for some wavelengths, we have to use telescopes aboard satellites. Even the way we collect the light can change depending on the wavelength. Here we will just overview the different observatories used for each band of the electromagnetic spectrum. These are telescopes operating as of 2013, operating at wavelengths across the electromagnetic spectrum. Observatories are placed above or below the portion of the electromagnetic spectrum that their primary instruments observe. So we're going to start out from the radio and then go towards the gamma. Radio waves can make it through Earth's atmosphere without significant obstacles. In fact, radio telescopes can observe even on cloudy days. In principle, we don't need to put radio telescopes in space. However, space-based radio observatories complement Earth-bound radio telescopes in some important ways. A special technique used in radio astronomy is called interferometry. Radio astronomers can combine data from two telescopes that are very far apart and create images that have the same resolution as if they had a single telescope as big as the distance between the two telescopes. This means radio telescopes can see incredibly small details. One example is the Very Large Baseline Array, which consists of 10 radio observatories that reach from Hawaii to Puerto Rico, nearly a third of the way around the Earth. Next, the Earth's atmosphere blocks much of the light in the microwave band. So astronomers use satellite-based telescopes to observe cosmic microwaves. The entire sky is a source of microwaves in every direction, most often referred to as the cosmic microwave background, or CMB for short. These microwaves are the remnant of the Big Bang, a term used to describe the early universe. Speaking of infrared astronomy has to overcome a number of challenges. While some infrared radiation can make it through Earth's atmosphere, the longer wavelengths are blocked. But that's not the biggest challenge. Everything that has heat emits infrared light. That means that the atmosphere, the telescope, and even the infrared detectors themselves all emit infrared light. Ground-based infrared telescopes reside at high altitudes in dry climates in an effort to get above much of the water vapor in the atmosphere that absorbs infrared. However, ground-based infrared observatories must still account for the atmosphere in their measurements. To do this, the infrared emission from the atmosphere is measured at the same time as the measurement of the cosmic object being observed. Then the emission from the atmosphere can be subtracted to get a more accurate measurement of the object. The telescopes for both ground-based and space airborne observatories are also designed to limit the spurious infrared radiation from reaching the detector. And the detectors are cooled to limit their infrared emissions. So you'll see that in a lot of telescopes, there is a thermal requirement that all the payload electronics and the optic components need to stay below a certain temperature. The James Webb Space Telescope is a large space-based observatory that is optimized for infrared wavelengths. Webb will be able to look further back in time to find the first galaxies that formed in the early universe and to peer inside dust clouds where stars and planetary systems are forming today. Visible light. So that's the stuff we can see the most. Visible light can pass right through our atmosphere, which is why astronomy is as old as humanity. Ancient humans could look up at the night sky and see the stars above them. Today, there is an army of ground-based telescope facilities for visible astronomy, also called optical astronomy. However, there are limits to ground-based optical astronomy. As light passes through the atmosphere, it is distorted by turbulence within the air. Astronomers can improve their chances of a good image by putting observatories on mountaintops above some of the atmosphere. But there will still be limits to how crisp their images will be, especially for faint sources. Visible light observatories in space avoid the turbulence of Earth's atmosphere. In addition, they can observe a somewhat wider portion of the electromagnetic spectrum, in particular ultraviolet light that is absorbed by the Earth's atmosphere. The Hubble telescope is perhaps the most famous optical telescope in orbit. Also in orbit is the Kepler Observatory. Kepler is using visible light to survey a portion of the Milky Way to discover planetary systems. So the question that I got regarding this topic is, why is there a need for telescopes to be placed on Mauna Kea when there can be ones placed out in space to collect data if so many indigenous groups are opposed to projects like these? So I think there are two different answers to that. On ground, we have the ability to return to the site, and it can actually be cheaper to make observatories on ground than in space. We have much more immediate access and real-time control of these observatories, and we can tweak them after the fact. But you're absolutely right that we have to be sensitive to indigenous groups. Yeah, that's not to say that we shouldn't be putting telescopes in space. I think there is very good reason for all the reasons I just listed why we should, but there still are good reasons to put ground telescopes on Earth. Okay, so here I took the image and I flipped it because I wanted to show you the atmospheric attenuation through the different wavelengths. So we just left off at visible, and we're going to go this way now from ultraviolet to gamma rays. The Earth's atmosphere absorbs ultraviolet light, so ultraviolet astronomy must be done using telescopes in space. Other than carefully selected materials for filters, an ultraviolet telescope is much like a regular visible light telescope. The primary difference being that the ultraviolet telescope must be above Earth's atmosphere to observe cosmic sources. X-ray wavelengths are another portion of the electromagnetic spectrum that are blocked by Earth's atmosphere. X-rays also pose a particular challenge because they are so small and energetic that they don't bounce off mirrors like low-energy forms of light. Excuse me. Instead, they pass right through. Unless they just barely graze the surface of the mirror, focusing X-ray telescopes require long focal lengths. In other words, the mirrors where light enters the telescope must be separated from the X-ray detectors by several meters. However, launching a large observatory is costly and limits the launch vehicles to only the most powerful rockets, the Space Shuttle in the case of the Chandra X-ray Observatory. And then finally, gamma rays. Not only are gamma rays blocked by Earth's atmosphere, but they are even harder than X-rays to focus. In fact, so far there have been no focusing gamma ray telescopes. Instead, astronomers rely on alternative ways to determine where in the sky gamma rays are produced. This can be properties of the detector using special masks that cast gamma ray shadows on the detector. Let's see. An instantiation of this is the Fermi Space Telescope, which was launched in 2008 and is designed to study energetic phenomena from a variety of cosmic sources, including pulsars, black holes, active galaxies, diffuse gamma ray emission, and gamma ray bursts. So hopefully that was good review from last semester when you all took space science and instrumentation. I hope I don't butcher this, but I'm going to attempt to explain spectroscopy. Spectrometers are the payloads for astronomical observations. So Spectroscopy is one of an astronomer's favorite tools to help understand the universe. Planets, stars, and galaxies are just too far away to be analyzed in a laboratory. Fortunately, very important information about these distant bodies is written in the light we detect with a telescope. A star emits light across the spectrum, a continuum. When white light goes through a prism, it forms a rainbow, its spectrum. In the same way as light from a star goes through the gas of a nebula, or even just the atmosphere of a star, specific colors or wavelengths are absorbed by the elements contained in the gas, producing dark lines over the continuum. This is an absorption spectrum. The energy that is absorbed by the gas is then re-emitted in all directions, also at the specific colors characteristic of the elements present in the gas, producing bright lines at certain wavelengths. This is known as an emission spectrum. The first astronomical application of spectroscopy was the analysis of sunlight by Fraunhofer and Kirchhoff in the early 19th century. It was expected that the white light emitted from the sun would produce a clean rainbow when passing through a prism, but for the very first time, a pattern of dark lines was also noticed. These unexpected lines were the fingerprints imprinted in the light by the different chemical elements interacting with it and are called absorption lines. So by decoding these absorption lines or barcodes, spectroscopy can reveal important properties of any body which emits or absorbs light. Spectrographs are fundamental pieces of astronomical instrumentation, and they are far more sophisticated than a prism. Instead of a simple rainbow, the output is a spectrum in which the light is more dispersed than in a rainbow. The spectra are recorded on CCDs or CCD detectors, and finally saved in computer files for further processing and analysis. The spectrum of a star or any astronomical object not only reveals the presence of certain chemical elements, but also informs about the prevailing physical conditions, such as temperature and density. Spectra can also tell us about motion by using the Doppler effect. This effect is used to discover extrasolar planets, and a similar effect allows astronomers to measure the distances to galaxies. Spectra also contain information on the magnetic field present in the object, the composition of the matter, and much more. A spectrometer itself consists of three main components: an entrance slit, a grating, and a detector. Okay, the last category of science that I want to go over is planetary science. Since we never orbited Europa and this mission is upcoming, I thought the Europa Clipper mission would be a good example of what kind of broad science we would do when visiting an entirely new planet or place, and represents the state of art when it comes to science instruments. For Jupiter's moon Europa, scientists have some big questions. That's why Europa Clipper will carry a suite of instruments more advanced and sensitive than anything that's ever been explored on this Jovian moon before. Researchers don't yet know if Europa hosts environments suitable for life to exist, so the spacecraft won't carry life-seeking instrumentation. Europa Clipper must first answer other questions. Does Europa really contain an ocean beneath its shell of ice? How deep is the ocean? Does the chemistry of the ocean seem friendly for microbes? Is Europa's ice shell tectonically active, allowing the moon's surface material to make its way to the ocean, and vice versa? Perhaps enriching the ocean with oxygen-rich molecules from above that could serve as food for organisms? To answer these questions and more, Europa Clipper will be equipped with cameras to map the moon's surface at high resolution, measure the heights of surface features, produce stereoscopic images, and seek evidence of a geologic activity. The spacecraft spectrometers will study the composition of Europa's surface and the particles floating in space above it. An ice-penetrating radar will hunt for water within and below Europa's icy shell. A magnetometer will measure the strength and direction of Europa's magnetic field to determine how deep and how salty the ocean is. The spacecraft's dust analyzer will analyze tiny fragments of Europa blasted off the surface by micrometeorites. An infrared instrument will measure the moon's surface temperatures, seeking relatively warm regions where material may have erupted to the surface. Some of the instruments will also seek any material that may be spraying from the ocean into space as plumes. Analyzing that material would enable the spacecraft to analyze Europa's ocean composition without even landing on its surface. So here is a picture that you've been staring at for a little bit now of all of the different investigations and the associated payloads in acronym form. So we'll go to the next slide. So here is a view of the spacecraft with the associated payloads. There are a ton of payloads and acronyms galore. What I've done is I've colored the payloads in blue, which are spectrometers. But these spectrometers, they're not redundant. They're studying different bands of the electromagnetic spectrum. And then there are other instruments like IceMag, PINS, Reason, and SUDA that are not spectrometers, and I'll go into that some more. They're distinct payloads on their own. Let's start with the magnetometer. So Europa Clipper's magnetometer instrument will have sensors that measure the direction and strength of the magnetic fields in the immediate vicinity of the spacecraft. While compasses and magnetometers are both capable of detecting magnetic fields, magnetometers used for scientific purposes are far more sensitive and precise, allowing scientists to accurately measure magnetic fields and study how they vary with time and location. The PINS, or a plasma instrument for magnetic sounding instrument, will have 4 sensors called Faraday cups. These sensors will measure the electrical current produced by plasma, which are charged particles, as it strikes a detector plate inside each sensor. The Faraday cup sensors will carefully measure the characteristics of the plasma, including its density, temperature, and velocity. Europa Clipper's radar instrument is called Radar for Europa Assessment and Sounding, Ocean to Near Surface, or its acronym REASON. The instrument will sound radio waves deep into Europa's ice, where they will bounce off subsurface features and return to the spacecraft. By recording slight differences in the signal's arrival time back at the instrument, REASON will create pictures of the ice layer's internal structure. And then finally, when microscopic dust enters Europa Clipper's Surface Dust Analyzer, or SUDA, it will pass through a series of grids that repel unwanted plasma particles and measure the dust's speed and direction. At the back of the instrument, the dust will strike a target plane and disintegrate into smaller ionized components, which will be pulled to an ion detector that will tell scientists what the dust was made out of. So I didn't give a totally comprehensive description of all the payloads that are out there, but hopefully this gives you a taste of the different payloads that could potentially be on a spacecraft. My challenge to you later in the semester is to create a compelling mission with a payload that fits within a very small spacecraft. So hopefully all of the payloads that we've described, technology demonstration, communication, and different sciences, those can help inspire something for your own mission. So small satellites are a whole game in themselves. So these aren't ordered in any particular way. They're not a certain category of mission. They are all common to the NASA INVEST program. NASA INVEST stands for In-Space Validation of Earth Science Technologies. So these are Earth orbiting. They're not necessarily looking at the Earth. They can be looking at the sun, for example. These are all small sats, and I think they're specifically CubeSats. So these will offer you the most direct translation of how you could incorporate payloads onto your 1U CubeSat. Although the challenge is that most of these are more than 1U. I think 3 is the smallest, maybe 6 is the smallest. But these are closer to the kinds of payloads that we would expect to see on your 1U CubeSat. So let's go with RainCube first. RainCube is a 6U CubeSat made by NASA as an experimental spacecraft. It has a small radar and an antenna. It was put into orbit in May 2018 and was deployed from the International Space Station. It is currently in orbit and it is used to track large storms. RAINCube is special because it is the first radar and active payload on a CubeSat. It demonstrates two new technologies in the K-band on a 6U CubeSat frame. It has a miniaturized K-band atmospheric radar for CubeSats and a half-meter K-band radar parabolic deployable antenna, which let's see. I think I have a video of it deploying. So this is definitely state-of-the-art, very innovative, cool stuff. There are also inflatable antennas that kind of look like a balloon. Yeah, neat. Okay. On the left is CSIM-FD, which stands for Compact Spectral Irradiance Monitor Flight Demonstration. It's a nanosatellite project of the Laboratory for Atmospheric and Space Physics, LASP, at the University of Colorado at Boulder to build a 6U CubeSat to take observations of the sun. SIM stands for Spectral Irradiance Monitor. And what I want you to see here is the general progression of miniaturizing this payload. What's very cool about, I guess, technology and science is that they're driving each other, where we have these smaller platforms and we have these smaller instruments, so we can do more with less, which is really exciting. See how big this initial instrument was in 2003. We have a version of it in 2018 that is a magnitude smaller, I would say. Okay, let's see. On the bottom right here, we have CubeRRT. CubeRRT stands for CubeSat Radiometer Radio Frequency Interference Technology Validation. It was made to demonstrate onboard real-time RFI processing, where RFI is radio frequency interference. So how noisy is it out in space? The CubeSat RRT payload has three critical pieces of technology: a wideband antenna unit, a radiometer, front end, and digital back end that performs the onboard detection and filtering of RFI. The main objective of the CubeRRT mission is to demonstrate the RFI mitigation technology on a flight-ready hardware in space. So another reason why people launch things on small satellites is to gain space heritage of components of interest. Some persistent mentality in space is that we don't like risk. So if you have flown a payload on a spacecraft before, then it's more likely to be adopted on other platforms and other missions. So the entire mission can be centered around just validating that this thing survives launch and operates in space. Okay, to finish up small satellite payloads, we have Tempest-D, and we have our own in-house HiTi. So Tempest-D is a temporal experiment for storms and tropical systems. It's a technology demonstration mission to enable millimeter wave radiometer technologies on a low-cost, short development schedule. Let's see, it was led by a professor at Colorado State in partnership with JPL and Blue Canyon Technologies, which stands for BCT. Awesome small company, by the way. They're really a game changer. So this company is trying to reduce the risk, cost, and development duration for a future Tempest mission. Tempest-D is the demonstration part of it. So let's see, what do I want to say? Tempest-D provides passive millimeter wave observations using a compact radiometer between the frequencies 89 and 182 gigahertz. Yeah, okay. Here you can see an instrument block diagram and an interface with the command and data handling side of the CubeSat. You can see the innards of the spacecraft here. All right, and then I'm going to talk about HiTi, which stands for Hyperspectral Thermal Imager Mission. also funded through the NASA INVEST program. HiTi will demonstrate how high spectral and spatial long-wave infrared image data can be acquired from a 6U CubeSat platform. The mission will use a spatially modulated interferometric imaging technique to produce a spectro-radiometrically calibrated image cubes with 25 channels between 8 to 10.7 meters at a ground sample distance of about 70 meters. So I just read off a bunch of payload specifications that don't particularly mean anything to me as an engineer, but as a scientist, those are requirements and specifications that you'll have to provide to engineers. And the HiTi performance model indicates narrowband NETs of less than 0.3 Kelvin. The small form factor of HiTi is made possible via the use of a no moving parts Fabry-Perot interferometer in JPL's cryogenically cooled BIRD FPA technology. So there we've got the imager, and then there we have a cryocooler, which is helping with the thermal control of the payload. So yeah, this is developed in-house at University of Hawaii. UH is a powerhouse when it comes to instrument development. The reason why we're branching out into aerospace is to support our scientists, because we have all of these instruments. Why don't we put them out into space and actually do the science? So we're trying to encapsulate the whole process in-house. Okay, so I'm gonna pause here if there are any questions. I'll review the questions that I've answered and the ones that I haven't. So hopefully I've answered these questions that are struck through already. If I didn't, please put it in the chat and I'll expand upon it even more. And then there are some questions that were not mentioned in any of the pre-prepared slides. So aren't there also UAVs being used in planned missions? Yes, so Mars Ingenuity is on the way to Mars right now. And it is a little copter that will do a little bit of scouting for the Perseverance rover. And then a planned Titan mission has Dragonfly, which is an octocopter to fly on the surface of Titan. And then I got a question about, will the Earth's extinction date come before or after the sun's death? So I did a little bit of research and I asked some scientists. Definitely Earth is going to be extinct first, but it depends on how you define what extinction is. I think if we're talking about the biosphere, pretty much the biosphere's extinction is going to be due to our Earth's inner core activity diminishing, which means that the magnetic fields will not be as protective. All at the same time, the sun's luminosity is increasing, which leads to the atmosphere being stripped. So by that definition, definitely Earth first. I think still, if we're talking about Earth as a rock that's floating around the sun, that might be blown to smithereens before the sun as well, depending on asteroid projectiles. Yeah. Okay, and then finally, a comment about I guess a change in perspective of wanting to be on Mars as soon as possible. What I will say about this is that the perspective has changed from Mars to the moon. And it is definitely true that Mars has a higher, I would say, activation energy or a higher delta V needed to get yourself off of the surface than the moon does. And so that's a very compelling reason to have a gas station or renewable resources on the moon instead, because the activation energy or the delta V necessary to escape the orbit of the moon is much less. And we just figured out recently that the moon has water, which we can use as fuel. So with that development in recent past, there's why the mentality has changed. Okay. Wow, time really flew.